Good morning everyone. As in last lecture, we have started with the revision of chapter magnetic effect of current. Okay, so we'll continue further magnetic effect of current. What we have discussed in the first lecture is Oersted experiment, how it has been discovered. After that, magnetic field lines of a bar magnet and how to draw the magnetic field lines using magnetic compass as well as using iron filings. So we'll continue further now. This is like we have done what are magnetic field lines. For example, if this is the bar magnet, then magnetic field lines start from north, they end up at south. So their direction is always from north to south. It is like this. Wherever they are congested, there the magnetic field is strong. Tangent drawn to them at any point will give you the direction of magnetic field. They never intersect each other, because if they intersect, then at the point of intersection we can draw two tangents. Means there are two directions of magnetic field at a single point, which is not possible. Okay, so these are magnetic field lines around a bar magnet. Now let us see what kind of magnetic field line pattern is obtained when we are having a current carrying conductor. Because what Oersted proved that whenever there is current through a wire, it behaves like a magnet. Now first we'll take a straight conductor. Like suppose this is a straight conductor carrying current. Now I'm not showing here battery, emitter and all which is providing current in that. You can draw it like this. Now suppose this is the straight wire, it is carrying current in upward direction. Now what is the pattern of magnetic field lines around this wire? So how the pattern has been studied experimentally. This wire is passed through a cardboard. Like you take a cardboard piece and you pass the wire through that cardboard, pierce it into that cardboard. So something like this structure is obtained. Okay, then pass the current through the wire with the help of battery, key, emitter and all. Then sprinkle the iron filings. So iron filings, they arrange themselves in this pattern around the current carrying wire. From that we have an idea that magnetic field lines around a current carrying straight conductor is of concentric circles. That pattern is of concentric circles. Concentric circle means these all are the circles with center at one common point. And later on it is given that how to draw the magnetic field lines around a straight conductor. We can use right hand thumb rule, that if thumb is pointing in the direction of current, suppose this is pointing upward, so we are taking this direction, thumb is pointing in the direction of current, then curl your fingers. Curling of finger will give you the direction of these circles. Like if my fingers are curling in this direction, means they are moving this way. That is anti-clockwise, because clock moves in this direction, so they are moving anti-clockwise. Means the direction of magnetic field lines, they are circles, but circles are anti-clockwise. So how to draw it on the notebook? Like here, these kinds of circle, when they are close to the wire, of course these lines are crowded. But as you move away from the wire, the distance between the lines has increased. Reason being, as we move away from the magnet, magnetic field decreases. So this is our magnet. As we move away from the magnet, magnetic field is decreasing. And these arrows show us the direction of rotation, anti-clockwise. Thumb is upward. Similarly, if it is pointing in downward direction, like this, like thumb is pointing downward direction, then curl your finger. You can see it is in opposite direction, clockwise. So in that case, you can draw. So in exam, always draw with scale, pencil. So you always draw neat diagrams. So this is the direction of magnetic field lines around a straight current carrying conductor. Now on what factor this magnetic field depend? Magnetic field we always denote by B. It is directly proportional to current. What does it mean? If we increase the current, magnetic field will also increase. It is inversely proportional to distance from the wire. As we go away from the wire, magnetic field will decrease, because it is inversely proportional to distance. Okay, so these are two factors on which depend. If we increase the current, strength of current is increased, means more magnetism is there, magnetic field is high. But as we move away from the wire, magnetic field is decreased. Okay, this is magnetic field line patterns around a straight conductor. Now suppose the conductor is circle in shape. Like for a circle, we need two ends to pass the current through that circular loop. So you can draw like this. This is the circular loop. Now here current is going through this end. Suppose it is connected to positive of the battery. This end is connected to negative of the battery. So it is like this arrangement. Current is going in and from here current is coming out. Then how to draw magnetic field lines? This much portion we can consider it like this half. We can consider it like a straight conductor. And for this, when you point, current is going in upward direction. Then curl your fingers. See, this is the direction. And here current, you can assume current is going in downward direction like this into the paper, and these are going outwards. Now how to draw this? If we consider this as the straight conductor, we know around a straight conductor the lines are circles, concentric circles. As we move away, the distance between the circles is increased because magnetic field is weak. Now what is the direction? Current is up, so it is anti-clockwise. Okay, now here current is downward, so they are clockwise like this. So again circles, but as we move away, the distance has been increased. Okay, so inside, like there will be bigger circles. I'm having less space here, that is why I'm drawing like this. And in the center exactly, we can draw a straight line. They should not touch each other, they should not intersect each other. Okay, so like this straight line we can draw in the center. So in the center, where is the net magnetic field is pointing outwards, like this is upward. So net magnetic field is in this direction, in the center. Okay, you can consider the loop like this, vertical. ऐसे consider कर सकते हो, the loop is like this, vertical. So magnetic field is into the paper. If this loop is vertical, magnetic field is into the paper. What is the direction of current in the loop? It is current in the loop. See, it is going from here, it is coming out from here. So current in the loop is in clockwise direction. When current in the loop is in clockwise direction, then magnetic field at the center is pointing into the paper. We considered it like this. So magnetic field is into the paper. These lines are going in. Now similarly, try to draw magnetic field line patterns when the current in this loop is anti-clockwise from here to here. And send me this pattern. Those who have done this, those who have seen this video, send me the pattern of magnetic field lines when current in circular coil is in anti-clockwise direction. And what will be the direction at the center? Okay, you all will draw this and send me WhatsApp. This is about magnetic field lines in a circular loop. Now in a circular loop, whenever like the phase in which current is moving in clockwise direction, that face of the coil is acting as south pole. Okay, like a bar magnet has pole at its ends, a magnetic loop has pole at its faces. Now here, if it is moving in clockwise direction, this end is south. Now when you turn the paper, you can see here the arrow. The arrow is in anti-clockwise direction. So its backside will act as north. When you see from the front direction, it is south. But when you turn the paper, it is in opposite direction. You can see this is the arrow. So this face will act as north. It is like a coin, heads and tails. So here, this is south. And if the current is in anti-clockwise direction, then that face will act as north. So a circular loop has poles at its faces. Okay, this is all about the circular loop. Then here magnetic field, how it depends upon various factors. It is directly proportional to current. More is the current, more is the magnetic field. Again, it is inversely proportional to distance from the loop. Like as we go away from the loop, magnetic field decreases, and it is proportional to the number of turns. Number of turn means if we give it more number of turns, 1, 2, 3, 4, 5, 6, like you have seen a bundle of wires. If this has been a bundle of wires, then the magnetic field is strong. This is one turn. Agar 2 turns hoti, 3 turns, 4 turns, 5 turns, magnetic field is more strong. Okay, this is all about magnetic field in a circular loop. Then last is magnetic field in a solenoid. Now what is a solenoid? It is like you all have seen the spring. Okay, there is the coil of wire. So in a solenoid, the same kind of structure, but a wire, like a copper wire only, that wire is closely wound over any core. Or like suppose you will take an iron rod, then you just wrap a wire around that iron core, but the wire is wound closely, very, very close. They should not touch each other, but it is very, very close. Then this arrangement, this is called solenoid. The length of solenoid is more than its diameter. Diameter is this is the length. Length should be more. Now in this solenoid, we start passing the current by applying the battery. Now see from this end, positive end, when the current goes here. Now in which direction current is going? When you see from this phase, current is going in clockwise direction. It means this phase will act as south. So the opposing phase, when you will see from other direction, the current appears to be in north direction. So this end will act as north. So here poles are at the end, and when the magnetic field line pattern is observed, the pattern is same as bar magnet, north to south. Outside they are from north to south, but inside their direction is from south to north, and they are straight lines. So this is magnetic field line pattern around a solenoid, which is similar to a bar magnet. They are starting from north, they are ending up at south, and inside they are from south to north, like a bar magnet. Thus, a bar magnet and solenoid are similar in terms of their magnetic field line pattern. Similar magnetic field line pattern is obtained. Their poles are at the ends, like bar magnet has pole at its end, north and south. They are also having poles at their ends, north and south. Inside that, magnetic field is uniform because they are parallel lines. Parallel magnetic field line means magnetic field is uniform. Similarly, inside a bar magnet, magnetic field is uniform. So these are the similarities between bar magnet and solenoid. But what is the difference? Like here, see, in solenoid, if we change the direction of current, like suppose positive terminal here, negative here, then the poles get interchanged. North will come here, south will come over here. But in a bar magnet, we can't interchange the poles. They are fixed. Similarly, in a solenoid, we can increase its strength. Magnetic field आप increase कर सकते हो, but because again it depend upon I, current, कितना current pass कर रहे हो, it depend upon the number of turns, कितनी turns आपने दी है. More is the number of turns, more is the magnetic field. More is the current, more is the magnetic field. So we can change its strength, but we cannot change its strength. So its strength is fixed, but its strength can be increased or decreased. So these are the differences between a bar magnet and a solenoid. So generally in a long solenoid, magnetic field is constant. At ends, it just reduces to half because end point पे जाके here there is nothing. यहाँ end पे जाके here there is nothing. So center तक means up to ends it is almost constant. Ends पे जाके exactly half हो जाती है. Suppose inside the magnetic field is 50, so ends पे आके it will be just 25. So this is like magnetic field pattern inside the solenoid. But up to your level, up to your syllabus, you can write magnetic field inside the solenoid is uniform, constant. So there are certain differences between solenoid and a bar magnet. So you all have to write what are the similarities, what are the differences in bar magnet and solenoid. So along with that diagram, you will send me the same. So this is all about magnetic field lines around a current carrying conductor. So this is the end of one topic. We have used right hand thumb rule always to find the direction of magnetic field lines around a straight conductor or around a circular coil. Same rule is applied here, that is why this pattern is obtained. Okay, so go through these topics again and again, and after that in your book start doing the questions which are given at the back. There are a number of questions. Start solving those questions, and you can send your doubt through WhatsApp if you are having doubt in any question. Okay, this is all for today. Thank you everyone.